All right, this video is going to help us with a process that's called partial fraction decomposition. Now, this is something that we can do with our pre-calc skills, but it's really something that's going to help you when you get to calculus and you start to talk about what's called anti-differentiation. Partial fractions is just a way to separate a rational expression, so such as x plus 7 over x squared minus x minus 6, right? That's the rational or fractional expression with variables here on the left, and separate it into two separate fractions with sort of minimal denominators going on. So how to kind of decide how to split that up and how to get those numbers on top to line up as well. And basically it just comes down to solving a system of equations. We just have to find a way to get to that system, right? So partial fractions can be described in a couple of different ways. Number one, if you have the numerator is of higher degree than the denominator, right? The first thing you're going to want to do is divide, right? If the numerator is bigger degree than the denominator, just go ahead and synthetically divide, get that polynomial laid out, and then the remainder is actually what we're going to perform the factoring or the partial fraction decomposition on, right? That remainder. So again, in order to do partial fractions, the denominator has to have a higher degree than the numerator, right? Otherwise, you should start by division, right? In that case, again, we take that remainder, we go down here. What we're going to do is we're going to factor the denominator by completely factoring it, right? Factoring it out into linear factors, sometimes also that are multiples or sort of the powers, right? And multiplicity. Or quadratic factors if that means going to imaginary numbers, right? Don't do linear factors of the imaginaries. You can leave those quadratic in there. Any linear factor is going to get split up into a bunch of fractions. Any quadratic factor is a little bit bigger, split up in a little bit larger way. We're going to do a single constant on top of each one of the linears, but we're going to do sort of a linear idea, right? Bx plus c on top of anything quadratic. Now that's described a little bit better here on this next page. First of all, if you have a very basic problem, we have a simple denominator got split up into an x plus 3 and x minus 2. What I'm going to do is set up an equation where I say, okay, one of my fractions then is a over x plus 3 and b over x minus 2. And my goal really is going to be to figure out what are a and b. If you have a factor that has multiplicity, right, it's to a power, what I'm going to do is I'm going to start off saying, okay, well, if that's x plus 3, I'm going to do a over x plus 3. But then I'm going to do another fraction over that linear function squared there, right? X plus 3 squared. And because it was cubic, I'm also going to do another fraction, again, a simple constant c over x plus 3 cubed. I'm basically going to count my way up, right, from first power all the way to the power of whatever my factor of my denominator was, right? If you do have one of those quadratic factors, as I described over here, right, x squared plus 3, what we would go ahead and do is do a separate fraction. X minus 2 just gets a constant on top, but x squared plus 3 gets a linear function on top. You get a bx plus c. And again, our goal would be to find a, b, and c. All right. Well, enough talking. Let's go ahead and take a look at an example. So we're going to walk through this one kind of quickly. The first thing I'm going to do is take my fraction that I have, and I'm going to go ahead and factor the denominator. So notice there's an x in both parts. So I'm just going to factor out an x. I've got x times x minus 3. In that case, what I'm going to do is separate into two fractions. I need a over x. I'm going to kind of ignore the 3 for now, but I'm going to have one fraction with a over x and one fraction with b over my other factor, my x minus 3. Okay? Now, here's kind of the big step. I want to get rid of all this rational stuff. I don't want these fractions anymore. So what I'm going to do is I'm going to multiply on both sides, right? Very simply, I'm going to multiply both sides by the denominator. So I'm going to multiply on this side by an x, right? X minus 3. And I'm going to multiply this whole side, right? Because I'm on the other side of the equal sign by x, again, x minus 3. On the left, that's going to give me just 3, right? Because basically it would cancel everything in the denominator. And then on the right, the first fraction, x, will cancel with that x out here. And what I'll end up with is a times x minus 3. The second fraction, you can kind of imagine the same thing. This multiplies onto the top. My x minus 3's cancel out, and I get just bx. Then, just to help us out a little bit, we're going to go ahead and distribute that a, right, into both parts. You'll notice that ax and bx then are like terms. They both have an x in them. So I'm going to reorganize a little bit. I'm going to say, well, hey, if a was times x and b was times x, then a plus b, right, is also times x. I'm just sort of group those two, and and factor out the x. That leaves me with negative 3a. That's more just a constant. It doesn't have an x variable in it, so it's its sort of own thing. Now here's the really tricky move. Here's what kind of usually throws people off. On the right, I have a linear function. If I knew what a and b were, right, if I knew their values, really I've got a linear term, x times a constant, and I've got a constant term, right? If I knew what a was, this would just be a number. Well, if x plus a constant is equal to 3, what I can actually say is that 0x's plus 3 were equal to a plus bx's minus 3a. So a plus b then must have been equal to 0, right? Because x and x would correspond. And negative 3a must have come out equal to 3, right? It wasn't multiplied by x. This is the constant. So what I can do is make a new system. I'm just going to line up my coefficient from x with x and my constant with my constant. A plus b equals 0 then, and negative 3a equals negative 3, which very quickly means that a equals negative 3 if I divide both sides by negative 3. Sorry, a equals negative 1. And if a equals negative 1, if I add that over to the other side, right, negative 1 plus b equals 0, that means that b must have equaled 1. Again, just solving the system here. Once you've got your system set up, you're just solving the system. Constant equals constant, or sorry, coefficient equals coefficient, constant equals constant, solve the system, and we would have an answer then that says, well, hey, our original fraction is equal to a over x, so negative 1 over x, plus b over x minus 3, 1 over x minus 3. You can check your answer just by taking that right side, and you would want to find a common denominator, right? So we would take x and x minus 3 and multiply them into the top, right, and bottom. Let's kind of get those to be constant or, common denominators. You could add the tops, and basically you get right back to your original. So you can check your answer by combining the fractions. You could also check it graphically just by graphing both of them, right? Type carefully. Careful with all your parentheses there. But you'll notice if you do graph that, you'll get the same graph both times. It'll trace out all three parts of this rational function, and they just sort of trace right on top of each other. They're the exact same graph. So again, you just get one single graph. I hope that helps you with partial fractions. Again, I'm going to show another example here in just a second. But really, let's go ahead and do that then. So write the partial fraction decomposition of this function. So feel free to pause the video now and you can attempt this problem. First thing that I'm going to do is, again, factor the denominator. And then in that case, let's go ahead and set up, right, our fractions then. So x minus 2 over x plus 3, x plus 1 is going to be equal to two separate fractions. I want a over x plus 3 and b over x plus 1. Right? I'm going to multiply both sides by x plus 3, x plus 1. That leaves me with just x minus 2 on the left. Again, if I put those into the top over here, I would cancel my x plus 3's, and I'm going to get a times x plus 1. And b, again, the x plus 1's would cancel, but I would get x plus 3. Again, I'm just multiplying on the top of every fraction by that common denominator. Again, in that case, we've got x minus 2 equals ax plus a plus bx plus 3b. I'm going to group the like terms. So again, ax and bx would really be x times a plus b. And again, we've got an additional a plus 3b this time. All right, that's all constant. There's no x in any one of those. Well, in that case, I'm going to go ahead and go up top here. I'm going to set up my system. All right. I know that the coefficient of x was a 1. So 1 must be equal to the coefficient of x over here, a plus b. In that same way, negative 2 was the constant. And again, a and b are going to form our constant here. A plus 3b forms that constant of negative 2. If I just subtract those two equations, or if I ran a negative, let's go ahead and do that. Let's run a negative through that top equation. Right? I'm just going to multiply both sides by negative 1. That way when I add them up, I'm going to find out that 2b equals negative 3, or b equals negative 3 halves, right? Negative 1.5. And in that same way, I'm going to go back to my original equation. a plus b, well, a plus negative 3 halves then was equal to 1. If I add 1.5 over to the other side, again, a is essentially going to be 5 halves, or 2.5. So our final answer then, right, would be, I'm going to go back to my fractions that I had set up here, right, just without, again, those extra parentheses in there. So let's go back and we'll fix that real quick. Again, it was a over x plus 3 and b over x plus 1. So basically 5 halves divided by x plus 3 plus b negative 3 halves divided by x plus 1. Now, if you remember with fractions and fractions, we don't really love that. So if I think of those denominators as being over 1, we could actually kind of multiply by the reciprocal, and you actually get 5 over 2 times x plus 3. And you'd have negative 3 over 2 times x plus 1, right? Those factors just end up in the denominator. But that basically is our final answer there. Okay. Now, a very quick reminder for you, just if you do have these different fractions going on, if you were trying to set up these formulas, right, as far as this goes, what would happen is, since we've got this fraction on the bottom, or this duplicate, right, this multiple, realize when we're setting up our separate fractions, we're going to say, okay, constant on top of that one, but I need to count my way up, x plus 4 and x plus 4 squared. There's how I'm going to do my two separate fractions. Again, if we're doing quadratics, just to be pre-warned, x plus 1 is a simple linear, so that's just a constant on top, but x squared plus 3 is quadratic, so we would say bx plus c when we went to set that one up. Then we would approach it the same way we did before. So again, very simply, for x cubed, I would have to have a over x, b over x squared, c over x cubed. Then I would add on, again, I would need a dx plus e, right? I'm just going to keep using more variables for the x squared plus 7. But again, I also need x squared plus 7 squared, right? So I'm going to need another, right, fx plus g. So that one would be, I'm sure, pretty fun to try to set up your system for. But just realize that's how you'd set up those bottom, portions, given kind of different various denominators. I hope that helps you with partial fraction decomposition. Have a great day, and ask your teacher if you have any questions. Have fun.